All right. So let's start here now. So as I said, some of the things you know already. I just using this book here to go through and do those notes here, right? Yeah. Right. So alternating, we have an idea that what the alternating looks like. Right? The alternating current, right? We know it looks like this here, right? Whatever graph is that? Sine graph, right? And here we have the general formula. This is the general formula for alternating supply. I is equal to I naught omega t. Omega is 2 pi f. Omega is what we call the angular frequency. Okay? Omega is the angular frequency. T is time. I naught peak value. Okay? And if they ask you to write it in terms of frequency, you can write I is equal to I naught sine 2 pi f. Right? That will take care of the omega multiplied by t. Okay? So if I ask you to write the same formula in terms of frequency, right? Take off omega and put 2 pi f. All right? Right? You know what peak value, you know what period, time for one cycle, frequency, number of cycles in 1 second. Right? What is peak to peak? What is that? Right? Peak to peak is here to here. Right? So your peak to peak value will be I naught minus your minus I naught, which is technically 2 I naught. Right? That is your peak to peak value, 2 I naught. Okay? Right? Right. So here's the little problem. The little problem is that alternating supplies are constantly changing. Right? To perform a calculation, we need an equivalent. Right? We need a DC equivalent of that AC value. And that equivalent is called root mean squared. All right. So the current and voltage supplied by a power station vary sinusoidally with time. As a result, the power supply also varies sinusoidally, right, with time. This means that there are times when the supply is 0 and times when it is maximum. In figure 8.12, it shows how the power supply by the AC varies with time, right? Right, now there is something called the root mean square value of our alternating current called the IRMS, right? It's the value of this steady DC which delivers the same power as the AC. All right, you have to learn that definition. So RMS is the DC equivalent of that AC value. Okay. By just find it, I naught on root 2. Okay. So IRMS is I naught on root 2. Right here, the power graph, right? That's what the power graph will look like. I was talking about a little while ago. Right here, one nice question. They asked us what the peak value, we could read it off. What is the RMS value? RMS is the peak value divided by root 2. What do you handle that? Yeah. And the frequency, well, what we have to do is say that 314 is equal to 2 pi f, because 314 is the omega. All right, and if you work everything out. Are you okay with that? So we have VRMS, we have IRMS, and as a result, we can find power. Right? Power will be IRMS by VRMS. Okay? And then we have to transform all the theory up on that. Right. Next thing that we had to focus on diode, right? What's a P type and N type? Remember that? Right. So these are the little things I'm going to run through. P type and N type. Simple things for you to once you read it once or twice. It's easy. Right? So we need to understand what is a P type material and an N type material, right? P and N are the keys. P and N are the keys, so you will know what it is. Let's just run through that fast. So semiconductors. See in there, right? So semiconductor materials, as the name implies, have conductivities that make them neither a good insulator nor a good conductor. Everything just in between. Pure elements such as silicon and germanium are called intrinsic semiconductors. In a silicon atom, there are 4 electrons. Yeah, you have to remember those things, right? In a silicon atom, there are 4 electrons in the outermost shell. In its pure state, all the electrons are held tightly in covalent bonds. In a process called doping, an impurity, which is the next element, is added to the silicon to enhance its conductive properties. If an element having 5 electrons in its valence shell is added to silicon, an N-type material is produced. You're saying why? Why I think N-type being produced? Something with 5 just been added. Something with 5 electrons has just been added. So it has 4, and you add something with 5. Something with 5, right? So when these 4 bond, what will happen? You will have an extra electron, right? So now you have an extra electron, so we call those N-type. Okay? Whenever you have more electron, N-type. Whenever you have less, P-type. P is like a hole. When an electron leave, it will make a hole. And that's a positive charge. All right, so 4 valence electrons are used in bonding, and therefore 1 is left. There is therefore an excess of negative charge carriers for electrons, which allows for conduction. On the other hand, if an element has 3 electrons in its valence shell, a p-type material is formed. The 3 valence shell electrons are used for bonding. This means that one bond is formed, is short per electron. This deficiency is referred to as a hole. Okay? There is therefore an excess of positive charge carriers, which allows for conduction. So p-type, you have an excess of holes, N-type, you have an excess of electrons. Okay? The amount of impurity added to the silicon is approximately 1 part impurity to 10 to the 6 pure. This means that no reason. Wait, 1 second. I'm just messing the next away here. I think in room 3. Yeah, it's coming down now. And the amount of impurity added to the silicon is approximately 1 part impurity to 10 to the 6 pure semiconductor. This means that only 1 in 3. None working? Yeah. I answer this one. No internet working now, sir. I'm here. I should have my laptop. Yeah, you can do that. I should have my laptop. Then come in your room. God is going to create there. Yeah. Tell them there. Sorry. So the amount of impurity added is approximately so and so. So the amount is so and so, and they give you the resistivity, right? In a pure metal such as copper, 3 electrons are the main charge carriers. So in pure electrons, we know that, right? The 3 electrons are the main charge carriers. So copper, each copper atom produces at least 1 conduction electron, right? And copper therefore has a low resistivity, 1.68. Okay, well, okay, with what a p-type and n-type. Now, when we bring a p and n-type together, we create a p-n junction, right? Remember, diode either allows current to flow, doesn't, right? So we have to take a look at what causes the diode to be in forward bias, what allows it to conduct, and then what allows it to not conduct. Anybody remember? Huh? Yeah, just bring them down. Coming up. Yeah. What you have to do? Remember? What controls that? What controls if it's forward bias or reverse bias? Right, no, I mean within the PN junction. how come a change in direction affects the PN junction so much that no current will flow through it? I forget already. The depletion region. When you have a small depletion region, the current can easily flow across it. When you have a high depletion region or large, the current just can't jump the voltage potential difference. So it can't go from one to the next and no current will flow. All right. So take a look at that PN junction there. So when the direction of the field current, the electrons move from the n type, they move and they fill up the holes. As a result of filling up the holes, the depletion region there is small. Right, just do my favor and I'll come back now. Just take a read of forward bias and reverse bias. Same handout, same thing is on page 82 and 83. I'll come back now. 82 and 83. Let's take a read there and I'll go through it. Give us 5 minutes. But it's good to go through it. Right. Sorry, they're online. Come back. Right. So consider what happens when a p-type is placed against an n-type material. The charge carriers in the n-type are the electrons, and they diffuse across the p-n boundary into the p-type material. The charge carriers in the p-type diffuse across, but really and truly, the p-type don't move, right? The holes here, when the electrons fill it, the electrons will leave a hole. So really and truly, the electrons that move it, not the holes. You understand that? When the electrons move from here to here and fill that hole, it'll create a hole. Right? So the hole's not moving. It's really the electrons that move it. Okay. This further the n-type material has lost some electrons and acquires a positive potential with respect to p-type material. This prevents further movement of electrons across boundary. The p-type material has gained electrons and acquired a negative charge with respect to the n-type. This prevents further movement of holes across boundary. After some time, the movement of electrons and holes stop because the potential difference across the junction, the potential difference is called the barrier potential, right? And the region around the boundary that has become depleted of electrons and holes is called the depletion region, right? Or depletion layer. The depletion region is about 1 micrometer. A diffusion current that occurs because of a difference in the concentration of holes and electrons, right? So it's important that you learn those definitions. You will see those things popping up. What's the diffusion current? And so on, right? Right here is the graph that we all know. This is the graph of current versus voltage, and that's the general shape of it. You'll recognize that after a particular breakdown voltage, nothing. Right? Nothing increases. There's no change at all. All right. And let's take a look at how fault bias will work.
I'll leave it in your inbox here. One, you can take the and that's all. Right.
Oh.
You read it about it and give the other person.
Right, fault bias PN junction. If it said it's connected across a PN junction, so that the positive terminal, make sure you remember that, right? The positive terminal connected p-type. That's fault bias, right? So the positive terminal is connected to the p-type and the negative terminal connected to the n-type. The junction is said to be fault bias. The holes in the p-type are repelled by the positive terminal of the cell. Electrons in the n-type are repelled by the negative terminal. As a result, the applied voltage is greater than the barrier potential, and electrons are pushed from the n-type to p-type. That's okay? So in negative charge here, pushing the electrons across the depletion region. Okay? The depletion region decreases in width. So all those little key things you will not, well, you may not remember this little paragraph. Remember the key things. Forward bias, positive p-type. Depletion region is small. Okay? And the drip current flows across the PN junction. Very important, right, Sarah? This is the current that occurs when the potential difference is applied across PN junction. Of course, reverse bias is the opposite, right? If a cell is connected across a PN junction, so that positive is connected to the n-type and negative connected to the p-type, the junction is said to be reverse bias. The holes in the p-type are attracted to the negative terminal, and the electrons in the n-type are attracted to the positive terminal. The electrons and holes move away from junction, right? And they make the depletion region larger in width. The barrier potential also increases. Eventually, electrons and holes stop moving and the drip current ceases to flow. The PN junction is referred to as a junction diode. The junction diode is used to rectify alternating currents. I mean, know that's already, right? Okay, so what's important is what is being connected on either side and what happens to to the depletion region. Okay, make sure you can explain that. Okay, you have your P type, your N type. Oh, right, you have the IV characteristic of the semiconductor diode. This is your graph. If you have to show it, make sure you can draw that graph, right? Right, and here we have transistors, right? If you have an N with N type, P type, N type. If you have an N type, P type, N type. If you have an NPN transistor, right? This is the way it's set up. If you have a PNP transistor, this is the way it's set up. Okay, remember the middle letter is always piece. All right, the top is the collector, bottom is the emitter. Right, this here is what you call a transistor. Okay, if they have to draw a transistor and label it, you have to draw that. Right, you have to draw this and be able to say if it's a PNP, how it looks. Right, characteristics of semiconductor diode, or you could read that junction transistor, or you could just read up on that small note, right? Rectification, we know about half wave, full wave, and smoothing, right? Here we have an example of a half wave rectification done by what? One diode, right? One diode, right? While it's forward bias is conducting, while it's reverse bias is not conducting. Okay, now we can move from half wave to full wave. This is full wave rectification. This positive conducted, this negative also conducted, positive conducted, negative conducted. That's okay? Everything conducted in. So therefore you have a full wave rectified, and by smoothing it out, it gets it closer to the DC. How you make it smoother? How you make it more like a straight line? Use a what? A larger capacitor, right? So this capacitor here has to be large. The larger the capacitor, the smoother it will be. Are you okay with that? Right. Let me just quickly explain how this works, right? That is your diode bridge. Just say a diode, draw a diode bridge. That's what they mean there. Here. You get message in me? Huh? You message in the notes? Right. So that's a diode bridge, right? How you draw it? Real simple, right? Diode bridge, you have to remember here and here, parallel. Here and here, parallel. Okay? It means the point in the same direction. You see that? And the way you can figure it out is you should remember this one and you should remember this one. Always remember that this has to be reverse bias, so when the current reaches here, it will continue along this path here. And once you figure out this, you know that this is the exact direction. So that is your diode bridge. Remember, everything you're listening to today might sound good, but you have to draw this thing over and see if you really remember where things should go, right? Okay, so analyst, why you hide in the back? Can't see it. Anyway, so here's how it works, right? So during an alternating cycle, let's say the positive cycle, here positive, here negative. Current going this way, right? When it reaches this junction here, it can either go to D1 or D2. It will not go to, well, some will go to D1, but D1 is reverse, right? So no current will flow out of D1. It will flow through D2. Because D3 is reverse bias, it will not go through D3, it will come down here. It will go through here if it needs to be charged, it will go through the load. When it reaches here now, it will not go to D1. Anybody remember the explanation why? Because the potential from S to P is from low to high. Right? S is lower than, and P is higher than S. Right? P is higher than S. Current flows from high to low potential. So it will not go to P because P is at a higher potential. It will come down to our and then come back here. It will not go up here because of the same reason. So it will follow that group path. It will come here, come here, come down here, come up here, come down here, come down here. All okay? That's during the positive cycle. But during the negative cycle, watch what will happen. Right? Watch what will happen, right? Here will become positive and here will become negative now. So the current will flow here. When it reaches here, it will go through T3, come down here. It will not go to D4, it will go to D1 and come back up here. So it will follow that red path, which means it will conduct in the same direction. You recognize that? It's going across the same direction across the load. So the load wouldn't know that it was alternating. The load will think it's behaving like that. That's called full wave rectification. And the capacitor now will smoothen it out. Right? The capacitor will not allow these negative phase, these decreasing phases here. So as the voltage drop, the capacitor will come on and supply the voltage needed to keep it constant. Okay? That's the way full wave is working. Everybody okay with that? So you gotta be able to draw that and explain it. Right? Functionally capacitor, you can read up on that, right? And you have some small questions here. Let me try one or two now. Well, we do look if we don't try. And then what I want to read up on these devices, right? LDR and microphone and power relay is good. So you don't want to see LDR and you don't know what LDR is. Right? LDR means the resistance dependent on lines. Okay? Also, you have to know what the symbol is. Because they're bringing these kind of nonsense now. You will see a whole question on what is that and what you use it for. And you'll be lost, but they spend all the time studying op amps and AC and digital. Those little things that you gotta know them, right? I think in 2019 or one of the years, they asked what this was. People didn't know, and they can explain the use of it. Okay? So those little things, go through it, right? I'll try one now. Try one like an hard-ish. But that's a transformer, right? Or the transformer. Try number 11. Right? And all that's left for us to look at is digital. Basically, you have to learn all the gates. I'm going to show you the two hardest gates, the flip-flop and the T-type. Right? And you're done. Right? So it takes, how long will it take? About 3 hours to do all this? You should be able to sit down for 2.5 hours and do the same thing. Right? Spend time, make sure you know everything in module 2. Then go back and do the same thing in module 1. Module 3 or module 3 should be good. Right? I'll tell you what topics to focus on. Try now with 11. This. I don't know if it's problem. Go to the something do this, you might have just one of them. So that one, you go ahead and support. It's good. But it is very safe. Janice? Why? Why? Right, so we're going to percentage, so you can have an idea. The choice of the two things, right? In order to have to do 10. Have you and all you just for example, right? And you have two questions here, you get two rights. There's two out there. That also true. And there you go. Easy. See. Right, there's one thing though that I want to show that keep an idea with that value. That's not it looks out. Not it looks out. I'm sad to remember something. Okay. 27. Based on how the sounds the problem about like very that something like that. Very that as well. Oh, I will send it to your correction. Right? It will happen. But the thing is for the real one, I would. The forward, the element. The other, the other doors. Correct. Not to do. Let's see.
It's against. Frequency.
I just doing one of those crucial one things in our box. I mean, digital and that. That's the idea. Okay, that's my favorite one. Not fancy, man. You have? Just the opposite, that's the full two things. All right, so they gave you current, they gave you the I naught value here, and they gave you omega 377, right? Find the frequency. So we know that 2 pi f is equal to 377. So f is equal to 377 and 2 pi hertz. What's the RMS current? I RMS is equal to your I naught. I naught is 8.2. Oh, by the way, you recognize in these past papers, they like to trick you with units, right? So be careful and read your units properly. Okay? Look out and see if it's microamperes or whatever it was, right? Pay attention to your unit. Don't just get excited looking easy. Pay attention to the SI units. Right? That is the IRMS. And then given that the mean power dissipated in the resistor cannot exceed this, what's the minimum value for R? So we're going to use P is equal to I squared R. Okay? R is equal to 350 over. It's mean power, so you're using the RMS value. So you're using whatever this was, right? 8.2 under root 2 squared. Okay with that? Yeah? Mean power dissipated. We know how to find power, right? And it's mean, so they're talking about RMS values. And then make Aristotle formula. All right, so again, even if you found that was hard, if you know the formulas of power, you'll recognize that the only one you could use is P is I squared R or P is B squared on R. Okay? You can't use B squared on R because you don't know B. Are you okay with that? All right. The last thing I want to go through, some of the up amps, right? Sorry, some of the calculations for, sorry, the explanations for digital. If you look here on the whiteboard, well, I'm not seeing there. Right? So you have to learn a gate. I can't help with it. You have to learn your gates, right? You have 6 gates to learn, and some of them will be repetition. So you know you have 3 areas you have to learn. So it's just really 3 you have to learn, right? I just want to focus on the 2 main gates that you have to learn is the NOR gate. The NOR gate looks like this. And remember, real simple, a 1 always gives you a 0 for a NOR gate. That's okay? So the input is 1 1 1 0 0 1 0 0. All these ones here will give you a 0. 2 zeros giving you a 1. That's a NOR gate, right? Bubble curve. Okay? Generally, you have to learn your gates. You have to learn your gates, you have to learn your how to add and things, right? Those things not as difficult. But what is difficult is the bistable. Right? Some people don't understand the way the bistable is work. Right? You have 2 types of bistable. You have one from NORs and one from NAND. Once you understand the NOR, NAND is the same thing. Right? So the bistable looks like this. Right? The bistable looks like this. You have 2 inputs, I1 and I2. And the next input comes from the previous output. So this Q becomes the input here. This output Q hat, right? This output Q hat becomes the input for the one on top. That's okay? This op amp, this bistable, this logic, this circuit, right? Only works when Q, right? When Q and Q hat are opposites. So Q and Q hat are exactly what they are, opposite of each other, right? Q hat means opposite of Q. So it only works when Q and Q hat are opposites. That's not wrong, right? That's not wrong. Huh? Correct? All right, anyway, right? So these two outputs must be opposites. Now here how does work. Right? One of the special properties, right? One of the special properties of this circuit, it has the ability of saving the previous output, right? So it has the ability to save and latch, or latch. They both mean the same thing, right? Here's how it works. When you have a 1 and a 0, right? We can figure out the output. You have a 1 here and a 0 here, right? We can figure out the output without even having an input here. How we know that? Because we know a 1 in a NOR gate will always give me a 0. So a 1 in this NOR gate will give me a 0. No matter what this is, this will always be 0. 0 will come down here. 0, 0 into a NOR gate is 1. 1, 1 will still give me 0, so then this circuit is stable. It's stable because these two are different. That's okay? So Q is 0, Q1 is 1. What's your special property now? Remember, you can only save a previous output, right? So I am going to save this. And to save this, I am going to take this 1 and convert it to a 0. So I'm going to take this 1 here and convert it to a 0. 0, 1 into a NOR gate is what? Still 0. 0, 0 into a NOR gate is still 1 will still come back here and I still have the same output. So technically, I just save. That's okay? So that's the way save this work. Are you okay with that? Now for sometimes instead of bistable, you see the term flip-flop. Flip-flop means I could flip the output from 0, 1 to 1, 0. Right? By changing this 0 to a 1. So I'm flipping the input now to 0, 1. Watch what will happen. 0, I'm leaving this 1 here. Changing this to 1, right? So now 0, 1 will give me 0 come up here. 0, 0 into our NOR gators. 1, 1 into our NOR gators, 0. So stable. 1 and 0, so it's stable. Right? 0, 1 will give me 1, 0. That's okay? And if I were to change it to 0, 0, I will still end up with 1, 0. So 0, 0 will always save your previous output. 0, 0 save the previous output. That's okay? That's basically how the flip-flop works. There is one state that's disallowed. What state it is? 1, 1, and if I have 2 1s here, that's disallowed. Watch why. If I change this to 1, right? 1, 0 into a NOR gate will give me 0. 0 will come back here. 0, 1 into a NOR gate will still give me 0, 0. So I end up with 0, 0 here. I don't want that. That is not stable. Right? That is not stable. Flip-flop will not work. You okay with that? That's it. That's it. Bistable. Bistable has 2 stable states. The 2 stable states are 1, 0 and 0, 1. And in order to save these states, we use 0, 0. Okay? This whole thing can be redone using a NAND gate. Just remember, a NAND gate. What is something for a NAND gate? What gives you a what? A 0 gives you a 1. That's all. So it will just be the reverse. Right? 0 will give you a 1. 1, 1 will be saved. 0, 0 will be disallowed. That's okay? So you can do the same thing with NANDs instead of NORs. Yeah? So that is bistable. There's one more type of gate, T-type. This one easy. The T-type, this is a triggered output. So let's say every time we go from 1 to 0, I am going to trigger the output to change. I'm going to trigger the output to change. Okay? Every time the input goes from 1 to 0. So this is a 0, this is a 1, there's a 0, there's a 1, there's a 0. So the output starting at 0. My input is going from 0 to 1. Will that trigger anything? No, because my trigger is 1 to 0. It's not triggering this to change, so it stays 0. 1 to 0 now. 1 to 0 now is a trigger. So it triggering now the output to change to 1. 0 to 1, no trigger, so it's staying 1. 1 to 0, triggering. That's okay? So that's the way T-types and triggers is working. Okay, but you have to pay attention to what trigger is. Trigger is not always 1 to 0. Right? 1 to 0 is a downward pulse. It can also be a upward pulse. Okay? So that's it. We still have more things in module 2, but that's like logic gates and binary addition. Okay? So spend some time and go over these things and go over the past paper with solutions and do some more. Right? From now, next week Tuesday, I might do something and I might do module 3. So between now and then, you can practice out some of the ODMs, like 14, 15, 16, and the earlier years. Right? Bring them on, you can go through them. Even do them as a group, if you do better, that's a bit of right? But bring it time over here and go through it. All right, so that's it. That's it for revision. Spend some time now and get your thoughts together, make a little summary, right? You want to make a little summary of everything, right? Break up what module 2 was about and everything. Do a little flow chart and make sure you have something to work with. Okay? And start doing the question. You don't want to forget all of this. This video is not private, right? So you can go back and look at it. Right? It has everything. Go on the live and you will see everything. Module 3, module 1. Spend some time and go through it. Okay? Yeah, keep it.